So these will be the podcast notes on periodic table trends. So don't forget, a trend is different than a law. A law does not have an exception. Periodic table trends do have exceptions, just like fashion trends. Not everyone follows a fashion trend. So these notes are on a fancy word for describing these trends, which is called periodicity. And that really describes the trends that go across the periodic table. So what we're going to be doing is we're going to be drawing a bunch of really cheap periodic tables. Like something that does not even remotely, well, it sort of looks like the periodic table. And the first thing that I'm drawing here on this periodic table is I'm going to be representing the trend for atomic radius. Well, atomic radius is basically how big an atom is. Now, if you can explain how big an atom is, you can understand every other trend on the periodic table. So it turns out that our biggest element is in the bottom left-hand corner of the periodic table. And it gets smaller as you go across. So it gets bigger as you go down. Let me draw an arrow showing going down. And it gets bigger as you go from right to left on the periodic table. And don't forget, an atom is sort of like a sphere where you have a center, which is the nucleus. And the atomic radius is the distance from the center to the outer edge of that outermost electron in an atom. Now, there is a more fancy way that we use to describe atomic radius. And the way we describe atomic radius in a fancy way is with this thing called electron shielding. So if you can understand how electron shielding influences atomic radius, then you can explain everything about the periodic table. So basically, it's like two concepts and then you understand them all. So what I'm going to do is I'm going to draw a picture for electron shielding to help you understand it. I'm going to draw out an atom like lithium, okay? And lithium has an electron configuration, I'm going to write out the long way, of 1s2, 2s1, okay? And lithium has 3 protons, and it also has I believe it has closer to 4 neutrons, depending on what isotope of lithium you're working with. So let me draw a picture of it, and this time I'm going to draw pluses for my protons. I'm going to just draw blank circles for my neutrons. Okay. And now I'm going to draw out the electrons as E minuses, but I'm only going to draw them out to the right this time. So the first 2 electrons are in the 1s orbital, and they're relatively close. So I'm going to draw 2 electrons relatively close to the nucleus. Now, obviously, this is not to scale. Don't forget, even with these 2 electrons being really close to the nucleus, they're still really far apart. Don't forget my analogy of the nucleus being like a big Hummer truck and these being like little baby socks, way, many, 1,000 football fields away. So they're still a long ways away if you blew it up to life size. So anyhow, now let's talk about this outermost electron, which we call the valence electron. Let me draw it right here. All right, let's talk about the forces at play in the atom. Don't forget, like charges repel. Let me write this down one more time. Like repel, opposite attract. If you can remember those 2 things, that will help you understand electron shielding. So let's look at the forces at play. So we have protons next to each other. They're like charges, so they're repelling. So they're actually pushing each other apart. But just as strong, actually more strong, there's another force called the nuclear force, which is preventing those protons from pushing each other apart. Now, we're going to describe what's going on between these electrons and the nucleus. Well, they are opposite charges, so they attract one another. So these are electrons, which are negative, and this is the nucleus, which is positive. So there's actually a force pulling in these electrons into the center of the atom. But there's also a force between this layer of electrons, which is my 1s, and then this layer of electrons, which is my 2s. And these electrons are shielding this electron from the positive nuclear charge. So this electron is being pulled in, but it's also being pushed out a little bit from this layer of electrons. That's what we call shielding. I want you to think of the atom as layers, even though these electrons, we never know exactly where their location is. This is my first layer. Those are the inner electrons, which we call the core electrons, the inner core electrons. These guys are the valence electrons. So how do we figure out systematically, a way that we can always get it right, how much pulling there is from the nucleus and how much pushing back is there from this first shield? This is our shield here. So we have actually a formula to help us figure this out. The formula is ZEFF as a subscript equals Z minus S. Let's label what each of these things mean. So this is what we call the effective nuclear charge. Now you should remember from our previous unit that Z is the number of protons. And again, that's what Z represents here, is the number of protons. S is your shield. And your shield is based on how many core electrons there are. I should say inner core electrons. So let's do a comparison between lithium and another element to see which one is going to have a stronger, more effective nuclear charge. Now, let's remember that the effective nuclear charge is our pulling force. That's that pulling force, pulling the electrons in, the positive pulling in the negative because they're opposite of charges. So now what we're looking at is lithium, and we're going to compare lithium to another element, say carbon. And we're going to be comparing their effective nuclear charge. Let's not forget that effective nuclear charge is the protons minus the inner core electrons. So there's two pieces of information I need to know, the number of protons and the inner core electrons. So for lithium, I'm going to write out its electron configuration. I'm going to do the same for carbon, so it's 1s2, 2s2, 2p. Oh, carbon is, what is it, 2p2. And then I'm going to count their number of protons. And the number of protons for lithium is 3. The number of protons for carbon is 6. I'm going to count their inner core electrons. The inner core is everything that's not the valence electron. So the highest energy level I'm going to ignore. So I'm only looking at this and this. And they both have the same core. They both have a 2-electron core. So minus 2, minus 2. And the effective nuclear charge is positive 1 for lithium. And for carbon, it's positive 4. Well, what does this show? That carbon has a much stronger pulling force. And because it has much stronger pulling, what's happening is those outer electrons are being pulled closer and closer to the center of the atom. So going back to our cheap little, or at least my cheap little drawing of the periodic table here. Oh, there we go. What happens is that atoms get smaller and smaller and smaller and smaller as you move left to right across the periodic table. And that's because as you move this direction to the right, the effective nuclear charge is increasing because, of course, lithium's here and carbon's over here. So lithium, much bigger atom than carbon. Atoms also get larger as you move down. The radius increases as you go down and increases as you go left. It goes down because if I'm comparing, say, lithium to potassium, even though they have the same effective nuclear charge, if I was comparing these two, lithium and potassium, let me write out lithium's electron configuration. It's 1s2, 2s1, and then let me write out potassium, and that would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So they have the same effective nuclear charge if you do the subtraction that I showed up above, but the difference is that these are the core electrons for lithium. These are all the core electrons for potassium. Because of that, this has a lot more of a shield. So as you move down the periodic table, your shield increases, but the effective nuclear charge doesn't, and because the shield gets bigger, you have bigger atoms. So now we understand this trend about atomic radius. now what we need to do is apply atomic radius to explain other things. So the bigger the atom you are, different things happen to you. First off, it's easier to lose an electron. And we have a definition for losing electrons in terms of energy, and we call this ionization energy. And there's actually a trend for ionization energy on the periodic table. So ionization energy is the amount of energy needed to remove an electron from an atom. An example of this would be I have sodium, it's just a neutral charge. I remove an electron, it now has a positive charge. Ionization energy is the amount of energy it takes to force sodium to lose that electron. Well, the bigger the atom you are, the less you're holding on to those electrons. So going back to what I just previously drawn, the biggest atoms are in the bottom left of the periodic table. So the bigger you are, you have this huge shield that is protecting this outermost electron, which makes it very easy for this outermost electron to fall off. So it turns out on the periodic table, the bigger you are, the easier it is to remove an electron. So as the atoms are getting bigger, as you move left and you move down on the periodic table, the ionization energy is actually the opposite, because it's how much energy it takes to remove an electron. This guy's really easy to remove an electron from, so it has a low ionization energy. So the smaller the atom you are, it has a high ionization energy. Because of that, the trend is opposite of the radius. So the highest ionization energy are to the top right of the periodic table. So if you're doing a comparison between, say, this atom and this atom over here, and I asked you who has larger ionization energy, you would say the smaller atom. That's it. Now, there's one more trend that we have to describe, and that's called electronegativity. Electronegativity, you're going to learn, is probably the most important trend, and it's how much an atom is attracted to an electron. Actually, we'll say pulls electrons close to it. So some atoms pull electrons closer to it than others. So that actually has to do with effective nuclear charge, which is that ZEF thing. So let's draw another periodic table. Oh, I didn't do this one very well. Oh well, we'll make do with it. Remember again, the biggest atoms are on the bottom left of the periodic table. Alright, so this guy's barely holding on to its electron. So it's not pulling electrons very close to it because all of these guys, their effective nuclear charge is all 1. These guys, the effective nuclear charge is high. Because the effective nuclear charge is high, they're pulling electrons really close to them. So the most electronegative element on the periodic table is fluorine. There's an exception to this rule. The noble gases have no electronegativity. We pretty much ignore the noble gases when describing these trends because they are stable, which means they don't do anything. They don't change. They don't pull electrons close to them. They don't remove electrons. They don't add electrons. But fluorine is so close to being a noble gas, if it just adds one more electron, boom, it's a noble gas. So fluorine has the highest electronegativity. And because of that, it pulls electrons really close to it. So if I'm showing a bond between hydrogen and fluorine, this bond I'm going to have symbolize 2 electrons. Those 2 electrons are being pulled really close to the fluorine. So fluorine develops this thing we call a partial charge. We draw it out like this, sort of like a half-8. We call it a sigma and then a minus because it may not gain a full electron, but it at least pulls them really close to it. So electronegativity has the same trend as ionization energy. To the top right, the higher it is. So just in review of all of this, in review, electronegativity is to the top right-hand corner. Electron affinity is pretty much the same as electronegativity. It's discussed in the book, but we're not going to really use it in this class. If you have any other questions, please let me know.